Hi, I'm Michael Lossman of Great Scott Gadgets, and this is Software Defined Radio with HackRF. Lesson 4, Mysteries. Sometimes in this course, I'll explain a concept and then ask you to exercise your understanding of that concept. At other times, I'll give you an exercise of discovery with a very little explanation beforehand. And the Lesson 2 homework was one of those times. I hope that you were able to learn a thing or two from the Lesson 2 homework, and I also hope that it was something that could bring more questions to your mind. Today I'd like to go through that homework together and see what we can learn about GNU radio and about digital signal processing. For the Lesson 2 homework, I asked you to create a flow graph that looks like this. It has a signal source, a throttle block, and an FFT sink. Let's run this and make sure it works. And we have a single peak displayed in the FFT plot. Now, the second thing I asked you to do, question 2, was to answer the question, does the flow graph behave differently if you remove the throttle block? Well, one way to do that is to disable the throttle block, but then we have to connect these two directly together to satisfy their input and output. Now, I can't actually demonstrate this running for you very well, and I'll tell you why in just a second, but you may have noticed some different things happen when you tried this. Now, some of you may not have noticed anything, but some of you should have noticed that the display perhaps did not work correctly in the FFT sync. You might have had applications time out. In extreme cases, I've seen people have to reboot a computer, but that's pretty rare. It depends on how many CPU cores you have and how your operating system is configured. Let me show you one way to measure what's going on here. I'm going to open up a window running the htop command. Htop is a handy program for measuring CPU utilization. You can see I have 4 cores here, 1, 2, 3, 4, and overall my CPU utilization is fairly low. It's all kind of under 50%, and the average here is well under 50%. And if I start this flow graph, you should see that the CPU utilization goes up a little bit. Now you can see that I'm using a little bit more CPU. My average CPU utilization across these 4 cores is a little bit higher than it was before. And if I stop the flow graph, you should see it go back down a little bit. It's not a very distinct change, but you notice that without the flow graph running, I sometimes have a core or 2 at under 10%. And with the flow graph running, I was using a little bit more CPU. Now, if I were to remove the throttle block, or disable it and bypass it, then I would actually see this across all 4 cores go to about 99% or 100%. And all of my CPU utilization, all of my CPU power would be utilized. And most of it would be utilized by this flow graph. Now, the reason I can't demonstrate this to you is because the CPU utilization that I do have going on right now is for my video and audio capture. And if I chew up all my CPU in GNU Radio, then my video and audio capture don't work very well and I can't record this video. So this is a nice thing for you to try on your own and just verify using htop or your favorite performance monitoring tool. You can verify that running the flow graph without the throttle block uses all available CPU cycles. And why is that? Well, one thing you might experiment with is increasing the sample rate, the sample rate variable. If I were to increase this to, say, instead of 32,000, if I were to increase it to 32 million and still throttle it, then I'm using a lot more CPU power. Look at that. I'm using like 50% of my CPU or more. And the more, the higher you have this samp rate set to, the more CPU power you'll use. And the throttle block is the thing that actually controls the real-time sample rate. how many samples per second are processed by the flow graph, and how many samples per second are processed by your CPU. So if we disable that and connect these two directly together, this flow graph is no longer rate limited. This signal source produces samples as fast as it possibly can, and this FFT sync analyzes samples as fast as it possibly can. Now this may seem a little strange because the sample rate is configured right here in the throttle block. It's also configured right here in the signal source, and it's also configured right here in the FFT sync. But it turns out that this sample rate here isn't treated the same way by the FFT sync as this sample rate configuration in the throttle block. And this sample rate in the signal source is not treated the same way as the throttle block handles its sample rate. Only the throttle block affects the real-time rate of this flow graph. I find that very interesting, and it's something that's a quirk of GNU Radio that is important to learn, that this configuration of sample rate doesn't mean the same thing to every single block. Now, hopefully nobody had to reboot their computer to participate in that exercise, but if you do have trouble, you might just try adjusting the sample rate variable instead of actually removing the throttle block completely. Now, question 3. Does the FFT sync correctly indicate the frequency produced by the source? I'm going to close my HTOP window here, and I've reset the flow graph to its default configuration with a sample rate of 32,000 samples per second and a throttle block in place. I run the flow graph, and it shows me a single spike. Now this is, the FFT plot is showing me the output from an algorithm called the FFT. And we're going to talk about the FFT a lot in future lessons, but for now, all you need to know is that the FFT is an algorithm that analyzes some samples and tells us what frequencies are present in that chunk of samples. And it does this, the FFT plot does this repeatedly on its input and gives us a real-time display. Now in this case, the display is unchanging, and that's because the signal source is giving us the same samples over and over again. So it doesn't look like it's animated, but it actually is. It's just animated over the same data over and over again. So the signal source is set to a frequency of 1 kilohertz, and the FFT plot has a spike, and if we hover our mouse over it, it is right at 1 kilohertz. And if you look at this ruler down here, the ruler goes from negative 15 or so, maybe negative 16 kilohertz, to positive 16 kilohertz. And you can see that the peak, this very tall peak, is just to the right of center at 1 kilohertz, 1/5 of the way to this 5 marker. Now, the next question I asked is, what if the source and sink have different sample rates configured? Well, let's try something. Let's set the signal source to have a different sample rate. Now, normally I recommend that you always use a variable and have the sample rate the same through all blocks that are using that should be using the same sample rate. So here I'm going to intentionally violate that rule, and I'll set this, instead of setting it to 32,000, I'll set it to 10,000. And so now we have a mismatch between this sample rate here and this sample rate here. Let's see what happens. Now look at that. It looks very much the same, except this peak has moved over. Now this peak is at 3.2 kilohertz. It's closer to this 5 marker. Let's try a different sample rate and see what happens. If I set this to, let's say, 100,000, I'll add another 0. Now, oh, okay, now it looks basically the same, except this peak has moved closer to center. It's only at, what is that, around 300 and some hertz, not kilohertz. That's very interesting. It looks very much the same, except the peak has moved. Now, to understand a little bit better what's going on, I'd like to visualize this slightly differently. I'm going to use an instrumentation block WX scope sync. Now a scope sync is like an oscilloscope. It shows you the value of every sample over time. The FFT sync is going through some complicated algorithm to determine what frequencies are present, and it goes through a lot more computation than the scope sync. The scope sync simply plots the values that it receives on the time axis, and so it's called a time domain plot, where the FFT is a frequency domain plot. The domain is what we see on the horizontal axis. Now I'll execute this flow graph with both these syncs in place. And now the part of the FFT plot is off the bottom of the screen, but you can see the scope plot up above. And you can see, sure enough, we have this cosine wave, this blue cosine wave that looks similar to what we would expect based on the fact that this signal source is producing a cosine. And there are some other things that are interesting to note about this. Now, one thing is that there are actually two waves. There's this blue curve, and then there's this green curve. And up here it shows those as channel 1 and channel 2. Now, where in the world do we get a channel 2 from? That's kind of mysterious, isn't it? I think we're going to need to explore that mystery in the future. Now, I want you to take a look a little bit at what it looks like if I set this signal source back the way it's supposed to be. I'll just set this to samp_rate, which is 32,000 samples per second. Now let's look at it again in the scope plot. You can see actually that we're seeing more periods of the cosine wave here. And I want to show you something, this marker. By default, the scope plot connects the dots. It connects every sample point with a line that links one sample point to the next. And sometimes that's very handy for visualizing a signal. However, it can be very deceptive. Remember that we're dealing with a digital signal here, and the digital signal only has discrete values at discrete points in time. It's not a continuous curve. So displaying it as a continuous curve can fool us into thinking there's something there that it's not. So I often like to select dot large, which gives me a dot for every sample point. And now, aha, we can see the individual values that are being produced by the scope sync. And if you count them, you could see if you count from this peak to this peak, you should find that there are 32 dots, or there are 32 samples per period. Now look back at the scope, the signal source, and you can see this sample rate is set to 32,000 and the frequency is set to 1,000. That's interesting. Let's try something slightly different. Let's try setting the sample rate to 16,000. I'll set it to 16E3. And now, if I execute the flow graph and change this to dot large, look at that. We have fewer dots per period, fewer samples per period. And there's actually 16 if you count them up here. 8 from here to here, and another 8 from here to here. There are 16 in a complete period. And notice that this ratio, sample rate to frequency, is 16 to 1. Interesting. What if we were to increase the frequency? Let's increase the frequency here to 2,000. Now the sample rate of our signal source is 16,000 and the frequency is 2,000. So that's a ratio of 16 to 2, or a ratio of 8. And if we look at our dot large, hey, look at that. We have 1, 2, 3, 4, 5, 6, 7, 8 samples per period. So it turns out that this signal source produces a number of samples per period of its cosine equal to this ratio of sample rate to frequency. Now, and we could probably make this plot look exactly the same, and notice that the FFT sync here shows a spike at 4 kilohertz, which really isn't correct based on this number. But remember that it says 4 kilohertz here, and let's just do something kind of wacky over with the signal source. We currently have a ratio of 8:1. So I'm going to just look at this for a moment and just invent a number. How about like, I just type some random keys on my keyboard. I'm going to copy and paste that up into here and multiply it by 8. Now remember, you can type any Python expression in some of these fields. So this should work. This should be 738.923 kilohertz with a sample rate that's 5 times that many. Even though these are really oddball numbers, notice that the ratio is 8:1 because I just multiplied one number by 8. And if we execute this flow graph, it should look quite familiar. We have 8 samples per period in the scope plot, and the FFT shows a single peak at 4 kilohertz. The FFT looks exactly the same as it did before. Isn't that interesting? And the reason it does is because all that matters here, all that matters to the signal source, is the ratio of sample rate to frequency. And that tells us a little bit about what this sample rate configuration means to the signal source. We know what it means to the throttle block. What it means to the throttle block is that's the real-time rate that this flow graph should run. And the way that it implements that is by taking some input samples and then only handing out taking those same input samples and sending them to its output, but it only doles them out to its output at a rate equal to this real-time rate of 32,000 per second. Now to the signal source, the sample rate configuration means something different. The signal source doesn't care about real-time rates at all. All it cares about is the ratio between sample rate and frequency. And that tells it how many samples per period of a cosine wave it should produce. And it just keeps generating those samples as fast as the next input in the chain will take them. Now, there's one other sample rate configuration here in our flow graph, the FFT sync. There's also one here in the scope plot, but let's ignore that one for now. The sample rate in the FFT sync means something potentially a little bit different. So let us just reset this signal source to the original configuration. By the way, notice I tried to type 1K here. I'm going to show you what happens. I'll set my sample rate to samp_rate. If I type 1K, it doesn't like that. It gets angry at me. Now notice it uses a K as an abbreviation when it tells you what something is configured to, but when you actually type it in, you can type 1000 and then it'll say 1K here, or you can type 1E3 and it'll say 1K here, but if you type 1K, it gets angry. And that may seem a little silly because that is actually how it displays the correct value, but it is an incorrect way to configure it. And it tells you right here, value 1K cannot be evaluated. And the reason it can't be evaluated is because we're typing a Python expression. And 1E3 means something in Python, and 1000 means something in Python, but 1K doesn't normally mean anything to a Python program. So we'll set that back to its original configuration, frequency of 1 kilohertz, sample rate of 32 kilohertz. And we'll run it through the throttle block into the FFT sync. Everything should run exactly as it did originally. And let's just verify that. We get a single spike at 1 kilohertz. Now, if I were to change the sample rate over here in the FFT sync, let's say I set this to, let's do samp rate over 2. Let's see what happens now. Now look at this. I have one spike. It's just to the right of center, and it says the frequency is at 500 hertz. The frequency was divided by half. What if I set this to a much lower frequency, much lower sample rate, like samp rate divided by 10? Now we run this again. We get this spike just to the right of center, but it's much lower. It says this spike is at 100 hertz instead of 1 kilohertz. And notice, however, that the spike has not moved with respect to center. Take a look at that. Look how it just goes just up to the right of that T in the title of the graph. If I set this back to its original state, samp_rate, we see, sure enough, that spike points just to the right of the T. It's the exact same plot. The only thing that changed when we changed the sample rate was this ruler down here, and then the numbers that we get when we hover our mouse over it are based on this ruler. Nothing at all changed except for the ruler. We could set a wildly tiny value here, for example. We could put a sample rate, I'm not even sure if this will work, but let's try a sample rate of 1 and see what happens. How about that? Now we get a graph that looks exactly the same. This spike is just to the right of center, but it's telling me that this frequency is well under 1 hertz. It's showing me millihertz on my scale. It's an absurd ruler, but the actual plot is exactly the same. So that tells you something about what the sample rate variable or the sample rate configuration means to the FFT sink. To the signal source, all it cares about is the ratio, sample rate versus frequency. To the throttle block, what it cares about is the real-time sample rate that it delivers its input samples to its output at. The FFT sink, what the sample rate means primarily is simply the ruler at the bottom, across the horizontal frequency axis. There's one other thing, however, that is a quirk of this particular block that you might want to know, and that is if we set it very high, if we set the sample rate much higher, let's say we set it to 1 million, and everything else in the flow graph is configured to 32,000. So now it's set to be much higher. If we run this flow graph, notice what happens here. We don't get anything. Aha! Now we got something. Now it looks exactly like it did at first, or with all the other configurations. We have a ruler that's absurd. It's based on that sample rate configuration. But the spike that we see looks in the exact same place. Nothing changed about the actual output here other than the ruler, and there was a little bit of a delay when this flow graph started up. And the reason there was a bit of a delay is because of the way this FFT sink is implemented with refresh rate. By default, the FFT sink displays 1 frame of information. Think of it as a video display showing you 1 frame of information 15 times per second. That's what the refresh rate is, 15 per second. And if you assume that you're getting 1 million samples per second and you want to display some information 15 times per second, one way you might implement that is by dividing 1 million by 15 and then taking that number and weighting that number of samples before you display 1 frame of information. And that's exactly how the FFT sink works. So there's actually 2 things that this sample rate variable affects when you change it on the FFT sink. One is the ruler, the horizontal ruler, and the other is this refresh rate, because the refresh rate is based on counting samples. So if this sample rate here doesn't agree with this sample rate over here, then the ruler is going to be all wrong with respect to this frequency. If this sample rate here in the FFT sink doesn't agree with this sample rate here in the throttle block, then the refresh rate will be all messed up. So 3 completely different interpretations of what that sample rate configuration means to these 3 different blocks. But long story short, if you set them all the same, things generally work correctly. And that's why we use a sample rate variable, and that's why when you open up a new empty flow graph in GNU Radio Companion, this is the one variable that it gives you for free. Before you build any other block, you'll always have a sample rate block, because it's so commonly used, it's so useful to have multiple blocks in your flow graph all configured to the same sample rate. And confusing things happen when things are not configured to the correct sample rate. So having a variable, having one place to change it in multiple configurations, allows us to do something like this. Set this from 32 million to 32,000, change it to 32 million, and now all of them agree with each other and everything should work just fine. And the only thing we see difference is that this says megahertz instead of kilohertz, but otherwise everything should work just correctly. And so, long story short, use a sample rate variable, make sure that everything is configured properly using that variable. Now, we've explored a little bit with the scope sync, and it's interesting to note that sample rate means something to the scope sync too, and basically it's going to be the same type of story as we see in the FFT sync. So, question 3 was, does the FFT sync correctly indicate the frequency produced by the source? Yes, it did. It showed a spike at 1 kilohertz. And if the source and sink have different sample rates configured, it does not correctly indicate the frequency, but it does do the exact same analysis and produce the same looking output, just with a different ruler. So question 4. What happens if you configure the signal source with various frequencies between 0 and 16K, or 16 kilohertz? To do that, I would like to use I bet you know what's coming, I would like to use a GUI widget WX GUI slider. And I'm going to call this slider freak for frequency. Now I'll set it to a default value of 1000 because that was my original value. And I'll give it a minimum and maximum of, let's say, 0 to 16,000. Now it's happy with those parameters. 100 steps should be fine. And then I just want to go into my signal source and tell it, instead of using a frequency of 1000, it'll use a frequency of freak, referring to that variable. So it should still say 1K because that's the default value of this slider. But if I execute this flow graph, and I'll just disable this scope sync again for now, now I have something a little unexpected. Oh, you know what I did wrong? This peak looks like it's right at 0. It's just very, very close to 0. The reason is because I set my frequency to 1K, but my sample rate is set many times that at 32 million. So I forgot to change this back to 32E3 for this part of the demo. Here we go. Now everything's back to its original state, except that I have a slider for frequency. And so now we should see, there it is, that spike just to the right of center at 1K. And if I move this frequency slider, sure enough, the FFT analyzes the signal and is able to tell me exactly the frequency that's being produced by the signal source. I can move it around between 0 and 16 and everything works fine. If I take it all the way down to 0, I see a spike dead center at 0. So that tells us a little bit of something interesting. It tells us what the signal source is doing, or it tells us anyway that the FFT is actually changing its output depending on the changing input. And you can see a couple of interesting things that happen. One is, watch the delay as I move this from left to right. Do you see how it lagged? The FFT lagged behind my slider? Just a little bit. And that's because of buffering in the flow graph. There are samples waiting here to be throttled. There may be some samples waiting here for the next refresh period and so forth. There's a little bit of buffering that goes on at every little step along the way. Every input and output, every connection in the flow graph has a little bit of a buffer. And also you may notice that the flow graph looks a little, the FFT output, when I'm stationary, when I leave the slider in one place, it looks like one very tall spike. But while it's moving, funny things happen. And you see this wideband stuff going on over many kilohertz of bandwidth instead of just this narrow spike. And that's because of little changes that happen when there's an instantaneous change. If I change this by typing on my keyboard, you'll see an abrupt change where there were kind of two peaks all of a sudden. And if I move it with the slider, I'm actually doing that same thing except many, many times in a row. As the slider goes through each step, it makes an abrupt change in the signal. And the FFT has, I don't want to say it has a hard time analyzing it. It just is given data that are not consistent, that are not of a consistent frequency because they're changing. So during that little transition period, while the FFT is getting maybe just a little bit of one frequency and then a little bit of another frequency, you see a lot more frequencies appear here in the FFT plot. But then while it's stable, you see one spike. I think that's kind of interesting. Now, the next question, question 5, is what happens if you specify frequencies greater than 16K? So I'm going to go into my slider here, and I'll change its maximum value from 16,000 to 50,000. How about? And let's see what happens. So it looks the same when I start up with it configured to 1K. I can slide it down to 0. It looks fine. I move it up. I move it up. It looks fine all the way up to, let's see, 16. And then as I keep going, hey, it's the Atari effect. It wrapped around like playing asteroids. And it went past 0 again. It keeps going to the right as I move my slider to the right. And as I keep going, well, look at that. It wrapped around again. If I move my slider back to the left, there we go. It's doing the exact opposite motion it did last time as I was moving it to the right. And as when we get back down below 16K, things look normal again. This is very mysterious, isn't it? I find this quite interesting. How does this happen? We have this peak that moves, and when it hits 16K, you can actually see just a little bit of blue here and a little bit of blue here. It's actually kind of simultaneously positive 16 kilohertz and negative 16 kilohertz. And when we move past it, we're into the negative frequencies, whatever that means. And as I move up, I think if I get to exactly 32K, it looks like it's at 0 again. And now as I increase, if I were to increase it to, say, 37K, which is 32 plus 5, now it's at 5 kilohertz. Same thing as if I set this to 5 kilohertz. And notice how similar it looks. We have this tall spike. It goes just below 0 dB, it looks like. And if I just type in the value 37K, look at that. Nothing changed at all. The slider moved, but the FFT output, or the FFT analysis of the output, didn't change at all. Let me try that again. I'll just type 5K and hit enter. Look at that. There was no transition whatsoever. I think that's pretty interesting and kind of mysterious. Well, we're going to leave that as a mystery for now and move on to the next one. What happens if you specify negative frequencies? Okay, negative frequencies. We've seen the FFT is displaying negative frequencies to us, but what in the world does that mean? Well, I'm going to change my slider here. I'll leave it the same default we've been using all along, and now I'll set the minimum to negative 50 kilohertz and the maximum to positive 50 kilohertz. Now, if I execute this flow graph, it should start up exactly the same way. And I can move my slider to the right, and we should see the Atari effect. There we go. If I move my slider to the left, we wrap back around. And now we're in the normal region, perhaps. And if I go past 0, hey, look at that. Sure enough, if I configure my signal source, to give me a cosine wave of negative 10 kilohertz, then I get an output that's from the signal source that, when analyzed by the FFT plot, actually shows up as negative 10 kilohertz. This is quite mysterious to me, because think about it for a minute. What is a cosine? What does a cosine wave look like? If you plot a cosine wave, it looks like this, and it has a symmetry across the vertical axis. In other words, it's identical forwards and backwards. If you go horizontally, on the horizontal axis, if you go one direction, it's the same as if you went the other direction. It's a mirror image. So cosine of negative x is exactly the same as cosine of x. Or in other words, there's no difference between a cosine of a positive frequency and a cosine of a negative frequency. No difference whatsoever. They're exactly the same. Which tells me that the output of a cosine source running at 10 kilohertz should be identical to the output of a cosine source running at negative 10 kilohertz. But if we go back and look at our flow graph, you can see we have a signal source, and when we analyze it with the FFT sync, we get a difference between negative 10 kilohertz and positive 10 kilohertz. If I type in 10 kilohertz, that's how I configure my signal source using this frequency slider. Then the FFT says, yes, you have samples that appear to have a periodicity of 10 kilohertz. And if I type in negative 10 kilohertz, hit enter, the FFT says, that's different. That's negative 10 kilohertz, not 10 kilohertz. I find that to be extremely mysterious. Now, question 7. Does the plot indicate the presence of any frequencies other than the one produced by the source? Hint, use auto scale. Now, before I do this, I'm just going to set this back to the default, just so it looks the same as other people's graphs. And I'm going to use the auto scale button, or you could use the increase dB per division button. Look at that. Now what just happened was the scale, the vertical scale here in decibels, has changed. So it's showing us from 0 to negative 200. Negative 200 is a lot of decibels, right? Or it's a lot of negative decibels anyway. So what do we see here? We see one big spike at the frequency that we expect. But we also see a whole bunch of other garbage at every other possible frequency that the FFT knows how to display to us. That's mysterious. Now, this is a mystery that I think we can solve right now. Why would there be any noise at all? I would call this stuff noise. That's one way to think of it. First of all, notice how much quieter, or how much less powerful, how much lower in amplitude this noise is compared to the spike. We're looking at a plot that shows us 200 dB in the vertical scale. The spike is just around 0 dB, and this stuff is around negative 170 dB. Negative 170 compared to 0. It's kind of hard to express just how inconsequential all this stuff is. It's 17 orders of magnitude smaller than this stuff right here, which was the frequency we expected. 17 orders of magnitude, 17 decimal places. That's tremendously tiny and insignificant compared to the signal that we have here. However, think about this for a moment. We are synthesizing this signal in software. Is there any more pure way to produce a cosine wave than to synthesize it in software? And then we're just delaying those samples a little bit, or throttling them to a real-time rate, and then delivering them to the FFT sink, which analyzes those pure synthesized samples, and it tells us that there's a bunch of extra frequency components in addition to the one we were expecting. There's this noise. Now, in a real world system, in an analog system, with an actual antenna, for example, if we were receiving this as a radio signal, we would expect all kinds of noise. There would be radio noise over the air and interference, and there would be noise from the actual electronic device itself. On the analog electronic circuit would have some amount of noise, and we would pick that up when we digitize it, and we would expect noise from a real-world analog system. But do we expect noise from a digital system, a purely digital system? Well, let's think about this a little bit. And the thing I'd like you to think about is data types. Now, if you're a computer programmer, you probably know a little thing or two about data types. And I want to show you that data types exist in GNU Radio. If we were to go into this signal source and look at its properties, you can see right here, output type. And if we pull down this menu, aha, we can select a complex, a float, an int, or a short. Now, short in GNU Radio is a 16-bit integer, where it's an integer value that is represented, where every number is represented by 16 bits. An int is a 32-bit integer. A float is a floating point number, so it can take on values that are decimals, so it allows the decimal point to move around, and it's implemented as a 32-bit float. And a complex data type we're going to talk about later. Pretty soon we're going to have the talk about complex numbers. But what you need to know for now is that the complex data type is built on floats. So we're dealing with floats here even when we select complex. So we have an integer data type, another integer data type, a floating point data type, and another floating point data type. And the default is actually complex, which is maybe a little bit unexpected for some people. If we look at this FFT sync, we see this one only knows how to deal with complex or float. If we look at the throttle block, we can see that it knows how to deal with complex, float, int, short, or byte. And a byte is an 8-bit integer. So, if we were to represent every single sample as an 8-bit integer, that means there are only 256 possible values, because a byte has 8 bits. And each bit gets multiplied by the other in terms of how many values the data type can take on. So we get 2 to the 8th power for a byte. That's the maximum number of values that can be represented. It could be any number from 0 to 256, or it might be a signed byte that lets us take on values that are negative. But there are only 256 possible values that every single sample could take on. If we went to a short data type, well, that's a 16-bit integer. So there are 2 to the 16th power possible values. And of course, 2 to the 16th power is about 65,000, much bigger number than the 256 that we would get with an 8-bit data type. So I want you to think about it a little bit. If you were to plot a continuous signal and sample that signal, or try to represent that signal in the digital domain, well, what we do is we divide up the time axis into a number of distinct sample periods. And at each sample period, we measure that analog signal, or we choose how we're going to represent that signal in the digital domain. But we also are restricted on the vertical scale. We're restricted based on the data type that we use. If we have only a small number of bits to represent every individual sample, then we have to kind of create this grid. We have the time axis carved up, but we also have the vertical amplitude axis carved up into this grid. And then at every sample period, we have to represent something. If we're trying to represent a continuous waveform, we have to choose the digital representation that most closely matches that analog waveform. Now, a cosine wave, of course, is a kind of a continuous function, and when we approximate it in the digital domain, we're going to be going through a process like this, where we take discrete time values, and at each of those points in time, we have to take a discrete amplitude. And this process of restricting the sample values to particular points in the vertical scale is called quantization. And quantization introduces a little bit of error. Aha! Every time we quantize a signal, we introduce error, and it's called quantization error. So if we look back at our flow graph and we look at this, click the auto scale button and look at all this noise down here, if we were to have represented this as a different data type, then we should see that this noise floor is a lot higher. Like if we used an 8-bit byte to represent every sample, this noise floor would be much higher. If we use a 16-bit integer, then the noise floor would be somewhat lower than that. With a 32-bit float, the noise floor is way down here where we see all of this garbage around negative 170 dB. Can you think of a way that we might make that noise floor even lower? Well, it would be using a data type that has more than 2 to the 32nd power of possible values. So you could use, for example, a 64-bit double precision float. Now, that's not an option for us in GNU Radio Companion, but if you were writing your own digital signal processing software, you could use double precision floats to represent every sample, and you'd get more range in the vertical scale between your maximum value and whatever minimum value is going on here. There's some minimum value. In the case of an 8-bit byte, that minimum value is just the byte that has one bit set, the least significant bit. In the case of a 32-bit float, what exactly is the minimum value of a 32-bit float? How close to 0 can you get? I'm not exactly sure off the top of my head, but it's finite. There's a finite number of values, 2 to the 32nd power, which is about 4 billion. 4 billion possible values that every sample could take on if it's represented as a 32-bit float. So it's not arbitrarily large or small. It's very large or very small, but it's not arbitrarily large or small. Now, think about for a moment if this were a real-world RF analog system, we would have some noise floor to deal with. And it probably would be much, much higher than negative 170 dB in comparison to our signal of interest. So in the digital domain, we still have to deal with noise inherently from the quantization of every value that we're dealing with. But we get some control over that noise. We can choose, is this noise floor going to be up higher if we represented our samples with a smaller number of bits per sample, or is it going to be lower if we use more bits to represent every sample? And so we have this control or this power over the noise floor. That's something that you don't have so easily in the real world with analog RF signals. But within the digital world, we have that control. I think that's very interesting. Now, question 8. Try multiple signal sources added together. Let's try this. So I'm going to take this signal source and I will copy it and paste it. And this one I'm going to set to have a sample rate, or sorry, a frequency. I'll set this to the default of 1000. So I'll leave that constant. Whereas this other one, I'm going to leave as a slider. Maybe I'll even change that a little higher, just so they don't start out at the same frequency. Let's set this one to 5,000. So one's fixed at 5,000, and the other one is variable. If we add these together, and I'm going to do this with a math operator, we take the input of one signal source and add it to the other signal source. And this does a point-by-point addition. So it takes one sample from this source and then the first sample of this source, adds them together, and delivers that sample to the throttle block. Then it takes the second sample from the first source, the second sample from the second source, adds them together, and delivers that sum to the throttle block, and so forth. Let's try this. Now we see two spikes. Now remember, the FFT is getting every individual sample added together, and it's analyzing it and telling us what the frequencies are that were present. And if I move this around, remember one of those is fixed and the other one is being controlled, and it looks basically the same as it did before, except that there's this one peak in addition to the peak that I'm controlling. I want to show you what that looks like with the scope sync. This is kind of interesting. Look at this craziness. We have a frequency. If I control this, if I move this around, look at how wild that scope plot looks. How crazy that waveform looks. And yet, somehow, the FFT is able to look at this right here, what you're seeing, especially if you give it individual sample points. These are the data, these blue dots, that the FFT sync is analyzing and telling us, oh yeah, you have a frequency here at 5 kilohertz and you have one at 8 kilohertz. And if you move this around, things may not look very easy for you to analyze by eyeball. I mean, look at that. Could you eyeball that scope plot and tell me that there's 5 kilohertz and 8 kilohertz? But somehow the FFT is able to do that. So hopefully that gives you a little bit of a respect for what the FFT algorithm is doing for us. Because it's taking, now this one's a little bit easier to see. Do you see how there's this high frequency component up and down and up and down, and then there's this low frequency component? That's a little easier to see by eyeball, and sure enough the FFT shows us a 1 kilohertz and a 5 kilohertz. But when we have two different high frequency components, it becomes very difficult to kind of determine that by eyeball. And the FFT is able to take this list of samples, or this stream of samples, and turn it into this plot that tells us exactly what signals are present. I think that's really cool. So, one more thing I asked you to try, question 9, was try various waveforms instead of a cosine. Well, if I disable my additional wave here that I'm adding together, let's just look at what this looks like with a single cosine wave. And then we'll look at what it looks like if I try, let's say for example, a square wave. And notice you can select a bunch of different things. If I do a square wave and start the flow graph, now look, the scope plot, see that blue curve? It looks very square. If you look at the dots, it's a bunch of lows, a bunch of highs, a bunch of lows. It just goes back and forth square between two different values, which are 0 and 1. And now look at the FFT. Look at how many different frequencies are present. But notice that only two of them are very prominent. Remember, things that are below, say, 20 or 30 dB, below our signal of interest, generally are things that we can ignore. So there aren't very many peaks that are very high in amplitude. There's a lot of stuff that's down here, around -30 to -40 dB. That's very interesting. We'll explore that in a little bit more detail in the future, but I want you to recognize something, that when we have a waveform that has an abrupt change, it goes from 0 to 1, and then 1 to 0. When we have a waveform that has an abrupt change, we tend to get a lot of frequency components, or I would call this a lot of bandwidth, this width in hertz of our signal. Whereas if we have a smoothly varying function that looks sinusoidal, then we have very narrow band signal. If I set this to a cosine wave again, you can see our peak is extremely narrow, and there really isn't any other stuff going on at any appreciable amplitude because we have a smoothly varying function. And that's something I want you to remember. If the time domain plot that we see in the scope plot, if it looks smooth and comfortable, if it looks like you could lie down on it and take a nap, then you have a narrow band signal. But if you have a scope plot that looks really spiky or has sharp edges, then you have a wide band signal or something with higher frequency components further from zero. Isn't it amazing how much we can learn from this one simple flow graph? And we aren't even done yet. For the homework for this lesson, go to greatscottgadgets.com/SDR, and under Lesson 4 there are a couple more questions that I'd like you to answer about this flow graph. I'd like you to play with data types, and the complex data type in particular, before we have the talk about complex numbers. I hope to see you next time in Lesson 5.